Okay, so in today's lesson, what we're going to talk about is definite integrals. We're going to expand a little bit on the concept of the antiderivative. So we've been playing quite a bit with this symbol, and we have been putting some functions in here, 3x squared dx. And we have also learned how to do the antiderivatives of polynomials by doing the bumping up and dividing. So in this case, this one will be a x cubed, and then you will divide by 3, so 3 divided by 3 is 1. And plus the famous c whenever you do an antiderivative. So that symbol, basically all it's saying is, to just go ahead and take the antiderivative. However, this symbol does have additional meanings. So in today's lessons, we're actually going to go into the other meaning that it has, and that is that symbol, it actually means the sum. The sum of what? Well, that's what we're actually going to discover today. Okay. So before we go into the actual definition of that symbol, we're going to go back to the geometry skills you had you picked up on in pre-calculus. All right. So I'm going to raise this a little. Raise this here. Let me see if I can blow this up. All right. So as you recall from pre-calculus, you touch a little bit on geometric series and sequences. Right? So what I have right here is a Greek symbol. Its name is sigma, and it stands for sum. So you are summing something. Right? In this particular case, how this is generated, just to go back to the pre-calc, basically a small review, is that you would be starting from a 1, and you would be stopping at some point. In this particular case, you would be stopping at n. N stands for, it could be any number. You would be cycling like this. So you will be starting at 1, you will put it into whatever function you're working with. You will ask yourself, have I reached n? And if you have not, you will keep on spiraling until you get a stopping point at n. Now remember, this is a sum. So for every cycle that you go through, you will have to put a plus in between them. So your final answer for this, it would be the sum of each term that you have generated from this little sigma notation here. All right. So let's see how this is applied with actual numbers on here. So right here, what I have is basically a generator. It's a sum generator. So we're going to go ahead and start with 1, and we're going to plug it into the function. Now this function is a very, very easy one because it's just I. So you're starting with I being equal to 1. You plug it into the I. So you are generating a 1 because you just plugged in a 1 in there. Then you will keep on cycling, and then you will ask yourself, is 1 equal to an 8? Then it is not. So you will keep on cycling through the loop. So then you bump up the 1 to a 2. So now I becomes a 2. You put a plus because you're dealing with a sigma, and then you put the 2 there because that's what you generated. Then you will ask yourself, is 2 an 8? And then it's not, so you keep on cycling until you get to 8. So you will generate all these numbers. When you get to 8, 8 is 8, so you will stop there. So that breaks the whole cycle. Then you will add all these numbers, all these digits, and you will come up with your answer. So the answer for this sum here is basically just 36. Now, how is this convenient? Well, it is convenient because this might be a really humongous number, right? So you will fill up a whole sheet of paper with numbers if you just do it without the sigma notation. But this is very useful, very handy. So the bottom line is that this notation here is a short way of saying that you're summing up, in this case, digits, right? If you had a formula over here, You could also, plug it in and then generate numbers and then come up with each piece, and then the final product, the final answer will be the sum of all those pieces, right? And this is just another example. If I square, then you plug in a 2 because you started with a 2. So you do have a starting point, you have a finishing point, and you just keep on generating, and you come up with a sentence. So it's sort of the same idea. Now, how is this connected with the antiderivative? Well, this sigma notation means sum, and the symbol right here that we have been using for the antiderivatives, they actually have the same meaning. This is just a very cool symbol or stylized representing sigma. So if this kind of bothers you a little bit, just think that this means sum, because that's all it really means. Right? Now we're going to go a little bit deeper into this, and then I'm going to teach you exactly what we are summing up in calculus. So we're going to start with this problem right here, or question. Now remember when we were doing the previous example, this one here, you had a 1 and then you had an 8. Well, there's a name for this number right here on the bottom in calculus. We call this one the lower bound, and this one is the upper bound. So it's the same terminology that we're going to be using in this calculus question. So you are summing up something, and you're starting at 0 because this is your lower bound, and you're stopping at 5 because that is your upper bound. Okay. Now, this numbers right here do represent something graphically on the x and y plane, right? So we're going to do this question graphically first, and then in future lessons, we're going to learn how to actually compute or calculate the exact answer for this particular definite integral. All right, so we are summing up something. Well, I just gave it to you right here that we are actually summing up calculating area of a function. You might be saying, well, what function are we talking about here? Well, we're going to concentrate on this right here. Whatever you see inside of the integrand, that is the function that you're working with. So if this helps you, you can extract that and just call it y equals whatever you see inside of the integral, which is the integrand. So that would be a y equals x. So what I've done right here is I graphed y equals x. So y equals x is, it's a diagonal line, and it goes to 1, 1, 2, 2, 3, 3, 4, 4, and so on. Right? It goes forever, to the right and to the left. So that y equals x is basically the inside portion of your integral. Now, we don't know where this 25 over 2 came from. But fortunately, we do have the graph right here. So what we can do is we can compute this area under the curve and the x-axis. And this, whatever area you get, is actually the exact answer for this particular definite integral. Right? So in other words, an integral, by definition, is the area between the x-axis, between the curve. It could be a straight line. It doesn't have to be a curve, but between the curve and the x-axis. Now, why did I start at 0 and why did I stop at 5? Where do you think those numbers came from? Well, you're right. It actually came from the lower bound and the upper bound. So in other words, the lower bound and the upper bound are x values on the x and y plane. They will, in future lessons we're gonna switch them to y's, but for this particular lesson, they are x's. Okay, so that's the starting point and that's the finishing point. Put them there, and whatever function you have in here, that's the graph. And then that area would be actually the answer for that particular integral. Okay? So if we're doing this using geometry skills, this is a triangle, so I will just do base times height and cut it in half. Base times height divided by 2. And that's a 5, and that's a 5. So it's a 5 times 5 for the area divided by 2, complete area for a triangle. And that's how they get the 25 divided by 2. Right? Right? It's kind of cool to do it geometrically. Very simple shape because it's and it's an exact answer. Because that curve is just straight, so there's no gaps in between. Right? If it had been like a curve like this, and then we wanted to find the area, then we would have those little gaps in there. So that answer would not be so accurate if we use the triangle approach. Okay. This particular example, what we have here is a V of t graph. So this is a PVA problem. What we're going to try to solve here is we're going to see if we can figure out what the total distance is traveled by this particle, vehicle, whatever, between the interval of 0 and 5. Right? Now, before, in the second 6 weeks of the year, what we did was, in order to figure out total distance, we worked with the S of t function. So we were given some S of t, and if you go back to your notes, you will notice that we actually work with the EVT strategy, and we put t here, S of t here. We put endpoints. Basically, in this case, it would be 0 and 5. We also computed the critical numbers of S of t, and to do that, what we had to do was take the derivative of S of t. That would give us V of t. We would set it equal to 0. Maybe do some type of factoring, but whatever it took to get those critical numbers out. Critical numbers, by the way, come from the derivative being 0 or on the 5. But in either case, we had those critical numbers somewhere here. It could be 1, it could be 2, it could be none. Then the following step was to plug in the endpoints and the critical numbers into S of t. We will get some values for those. I'm going to make up some numbers in here so that you can just get an idea. 1, I'm going to say that this is 3 and this is 5. This is 8, 2, and 6. Right? So you will plug in those endpoints and critical numbers into S of t. You will come up with the y values. And then we say, well, my position at 1 was 8. My position at 3 was 2. So the total distance I traveled was a 6. And right here, the total distance was a 4. Traveled 6, and then I traveled 4. So my TD, or total distance, was a 10. Right? So that was a very elaborate process that we had to go through in order to figure out the total distance. However, we're bringing in additional tools now. So this process could be done much faster if we had additional tools, and that's exactly what I'm about to give you. Right? In order to do total distance in this particular graph. Now, this graph is very unique. It's very unique in a way because the whole graph is on the first quadrant. So it is above the x-axis. That's something that we are going to have to recall in the future because total distance and total displacement do have something in common when the graphs are on the first quadrant. Okay? But we are going to, don't worry about that too much because we are going to discuss that a little later on. All right? But for this particular case, so this is V of t. So if I were to compute the integral from 0 to 5, and basically from, I'm getting the 0 and 5 from the interval that they gave me, because that's what I want to compute. If I were to do this, and if I had the right tools to compute this, then whatever answer this integral will give me, that's exactly the answer. You don't have to go and go through all that table. So basically what this is doing for you is doing EVT in a really, really fast way. Now, do notice that for this particular problem, you don't need S of t, kind of like what we did with the table problem, EVT. But hey, if you're given S of t, you can always derive V of t and put it on here and then go with the future tools that you're going to get to compute this particular integral. Right? And again, we still don't know how to compute this, but we are going to do this geometrically. So I'm going to cut this in two pieces, and it will be an exact answer because it's a perfect shape. It's a triangle, it's a rectangle. 1, 2, 3, 4. 4 times 3, so that area is 12. 1 times 3 is 3, and cut it in half, so it's 1.5. So that whole area is 13.5, and that's what I have right here. So guess what? My total distance that I traveled here was 13.5. It's that easy, right? Geometrically. Even with algebra, it's quite fast. Okay. So anyone happy out there? No more EVT if you are given some sort of problem that looks like this. I do get some questions once in a while. You say, Flores, all those graphs that you're doing there are kind of rigged. You kind of designed them so that they, they're geometric shapes. But what if that curve it doesn't have like straight edges, it's literally a curve. How are you going to compute that? Because there's no way that we can, unless it's kind of like a circle, that we can come up with something like that really, really quick, or semicircle. But look at this example up here, the parabola, right? And again, it's only on the first quadrant. If we want to compute the area for this, so we will have a problem here doing this geometrically. So in calculus, mathematicians, how they approached this in the beginning was, well, I cannot give you an exact answer yet, but what I can do is I can approach this by cutting this into pieces. So this is the idea that they came up with. They said, well, let me cut this into shapes, right? So I can make little rectangles. All right, so you get the idea. And you might be saying, whoa, that approximation is not going to be that great. You're leaving a lot of, you're over approximating because you have more than what you really need, if you notice the yellow there, right? True. But it would still be an approximation, wouldn't you agree? Yeah. So it's better than not having anything. So we're going to use these strategies to approximate the area between the curve and the x-axis. This has a name. And there's 4 types of approximations that we need to learn for the AP exam, and that is the left approximation, the right approximation, the midpoint approximation, and the trapezoid. You will be responsible to learn all 4 of them. I do not know which one you're going to be tested on, but more than likely you will be tested on at least 2 of them. Okay. So why are you calling it the left, and why are you calling it the right, or the midpoint, or trapezoid? We're going to take one example, go through the process to see what the left approximation method is, or the left rectangular approximation. You might say, well, what is it? It's called rectangular. You'll see in a minute. The left rectangular approximation method, the right rectangular approximation method, or the midpoint rectangular approximation method, or the trapezoid. So I call them one Lram, Rram, Mram, and Trapm. Okay? So each one has an acronym for each particular method. Okay? I have an integral right here. And this is the exact answer. Now you don't even know where this 21⅓ came from. I gave it to you. Now the reason I gave it to you because we want to have some sort of way of comparing the approximations that we're going to get to see how close they come up with 21⅓. Okay, so we'll get to compare which approximation method is more accurate or closer to the actual answer. Let's start with Lram. So this is the left rectangular approximation method, Lram. Okay? So let's go through the process to see how this is done. Now, you do have some instructions here. So on the AP exam, they will literally tell you, use Lram or use Rram, right? They will tell you also into how many pieces you're going to cut this this area, right? They call it subdivisions, or I know they can use any type of terminology, but you will get in black and white on the exam literally into how many pieces you're going to cut this. Now right here, I'm telling you to divide particular interval. Now remember, we're going from 0 to 4. So I'm starting at my lower bound, which is 0, my upper bound, which is 4. And I'm going to cut this into 4 equal, keyword on there, equal sub-intervals, right? Oh, that was kind of like, that's easy, Flores. 1, 2, 3, 4. It's already made for us. Yeah, you're right. Okay, so here we go. This is one technique that I use, and that is 1, 2, 3, 4. So I have 4 sub-intervals. They're all equal, like they requested. Now they want me to use the left ram. So what you're going to do is you're going to make a point or dot on the left side of each line that you just drew. It must be touching the curve. Okay? So there's a dot. Okay? Only on the left side. Do not make the mistake of making a dot here, Pretend that there's a line right here and you're going to put one up there. No, that would be inaccurate. So the idea here is that you are creating rectangles. So from each dot, you're going to go to the right, and you're going to make a straight line. Okay? What is that going to give you? The first rectangle is going to be completely flat. So there you have it. You would be computing the areas for each particular rectangle. You're going to sum them up, and you're going to say, Flores, this is my approximation for that particular integral. That's the best that I can do with the information that you have provided. Okay? And that is it. Not that difficult. Right? Now you might say, oh, are they really going to ask me something like this on the AP exam? And well, they won't ask you to draw it, or I guess they could. I've never seen it though. However, they will ask you to do the setup for the approximation, and eventually they will also ask you for the actual computation for the approximation also. So what I'm going to do is I'm going to put additional information on this so that we can learn how to actually do the setup and maximize the points on the AP exam. So now remember, this function is x squared. So if this helps, put f of x equals x squared. Now I'm going to take one particular rectangle from here, and I'm going to see what sort of notation I need to compute the area. So I'm going to extract this. Only this one. Let's see if I can get a better marker, guys. So I'm concentrating on this one. Now we do know that the area of a rectangle is base times height. So the base right here is just a 1. Right? So I'm going to take that one right there. Area for that. So the width is, base times height or length times width, whatever you want to call it. But basically, it's a 1 for this right here, and there's a height. Now the height, you might say, well, I can see that it's a 4. You're like, whoa, that's just too easy. I can do all the other ones, sum them up, and I'm done. Yes, but remember, this is calculus. We need to show notation for them. We need to show them where these numbers came from, right? Now, where did this 1 come from? Well, that's just literally the 1. So there's no notation for that one. Quite simple. However, for the height, you do need to show where that 4 came from. Even though the 4 is correct there, you want to show something that looks like this. The 1 for the width, and for the height, you want to show f of 2. And you're like, ooh, where did that f of 2 came from? Remember, this is the f function, right? F function. So I can choose any value here, and this is where the dot is. So you're going to put it in here. What value do you see in there? That's a 2. So f of 2 equals 2 squared. So f of 2 equals 4. That's where the 4 is coming from. Okay? So what you want to do is, you want to concentrate on these little dots to get the height. And then you just multiply by the width. And that's how you would sum it up. Alright? So this is what we're going to do. I'm going to write exactly what I would write if I was taking the AP exam. I would write something like this. Integral from 0 to 4 of x squared dx. Approximately. Look at the symbol that I'm putting there. Because it's not going to be an exact answer. Using Lram. Equals. Now, equals in this case because the Lram is going to be the exact answer whatever I get on the Lram. Right? Now, I'm going to do the first rectangle. I'm paying attention to the height. Right? Now, what is the width of my first rectangle? Well, the width is 1. And what is the height? F of 0. I'm done with the first one here. Second one. What's the width? 1. What's the height? I'm paying attention to the dot. F of 1. Plus the width. 1. Times F of 2. So right here I have 1 rectangle, 2 rectangles, 3 rectangles, plus another 1 and F of 3. Right? F of 3 being the last one here. So that will be the last rectangle. And then this will get me 1 point on the AP exam. Just basically do it the setup. The rest is just quite simple. So that's 1 times height, which is 0, plus 1 times 1, plus 1 times f of 2 is 4, plus 1 times f of 3 is 9. So that's a 0, that's a 1 plus 4 plus 9, which gets me 14. Now you might be saying, oh, that's really way off compared to the 21 and a third. So what can we conclude from here? We can conclude that the approximation that we came up with is really a under approximation. So in Lram, it's under approximating. Now is it under approximating all the time? Or sometimes? Well, for that, we're going to have to think a little bit more. Do pay attention to the type of function that you're working, the curve, right? Now, this curve right here, it's a curve that is increasing and concave up, right? Increasing and concave up. So if you want to do approximations and you're doing Lram, so you make a dot, you make a dot, you can see that because it's increasing and concave up, then Lram will always be under it. So it will always be an under approximation. All right? So we are going to practice with this concept because that's also an additional point on the AP exam. So understanding which method of approximation gives you an over approximation or under approximation does help to get that free cheese point on the AP exam. And don't panic, we are going to practice with that a little bit more, right? But for right now, I do want you to be concerned with this setup for the rams, right? Okay, so here we have a mini lesson on, right here we're working with the right rectangular approximation, or Rram. Okay? And it's basically the same problem that we did with Lram. And again, same function, right? Same lower bound and upper bound, 0 to 4 of x squared. It's a parabola, increasing, opening up. and the exact answer is 21 1/3. So we're going to see how close we come up with 21 1/3. Remember, on the LRAM we got 14, I believe. So we're going to see if this one is much better or not. All right. They want us to cut this interval in 4 pieces using the right hand. The right hand basically being the Rram. Okay. So here we go. 1, 2, 1, 2, 3, 4. There's my 4 pieces. And since now I'm doing the Rram, I need to make those dots on each particular line that I just drew on the right side of each rectangle. So first rectangle, right side, second rectangle, right side, and right side. And you're going to make lines from those dots. And you're going to say, well, that's the dot right there. Let me make it to the right. Well, that's not going to work. Because then how are you going to draw this one? Right? What rectangle are you going to have? Are you going to do it like this? Then you're not using that dot up there. You have to use all dots. So you see where the missing link is right here? I used the wrong approach right here. I have to use all the dots that I just drew. So that approach was totally incorrect. I used the first one, second one, third one, and fourth one. I use all the dots. So there's my first rectangle. There you have it. You can see right off the bat already that this is going to be an over approximation. Why is this an over approximation? Because my graph is increasing and concave up. Would that always be the case? Yes, if you have this type of graph. Okay. So let's see if we can do the setup. Now remember, this is f of x equals x squared. Right? So that particular dot right there is going to be f of 1. That one is f of 2. That one is f of 3. And that one f of 4. You know, well, why didn't you do f of 0? F of 0, I don't have to do it because there's no dot there that I drew. So I'm just doing the ones where I have dots. Okay. All right, so the integral from 0 to 4 of x squared dx, it's approximately using Rram equals width, so that's a 1 for the first one. The height is f of 1 plus 1 f of 2 plus 1 f of 3. So I have 1 rectangle, 2 rectangles, 3 rectangles. Need one more. F of 1 is, you can extract them from here. That's 1. So this is 1 times 1, 1 times 4, 1 times 9, 1 times 16. So that's 1 plus 9 plus 16. All right, so that will give me a 10. 10, 26. Come on, Flores, that is way off the chart. Yeah, you can see that one is way higher than a 21 1/3, and that's why this is a over approximation. And it will always be true because this, for all the graphs who are increasing and concave up, right? You can see where we're going with this. We did the left, and we put the dot on the left side. We did the right approximation method, and we put the dot on the right side. So if we're doing the midpoint rectangular approximation method, you're right. We're going to put that dot in the center of each sub-interval, right? And that's how we're going to get the height for each particular rectangle. So we're still going to cut this into 4 equal subintervals, but using the midpoint hand. All right. So same process. Midpoint. So now I'm not putting the dot exactly on the line that I just drew. I'm putting the dot in the middle of the rectangle. Right? Dot, dot, and dot. And you're like, how am I going to draw the line? To the right or to the left? Well, you know, each one is going to be a rectangle, so there you go. So you're like, Flores, oh, look at this. I have a kind of like a little over approximation, and then I have a little gap right here. Let me color this so that you can actually see it. See this particular rectangle? It's a little over approximation, but then you're missing something here. So what do you think? Do you think it was going to be a better approximation than the left and the right? With the right, it was an over approximation for this one. With the left was an under approximation. For this one, you kind of like, you can't really tell, right? Because you don't know if that one, that little piece that is an over approximation will actually fill that piece right there. You can't really make that judgment, right? But I have a feeling that it might be a better approximation than the left and the right. All right, so we're going to compute these and see how close we come up with to the 21 1/3, right? So a little bit faster now. 0 to 4, x squared dx, it's approximately, using Rram, equals. Now the width, we already know it's a 1 for all of them. But what is the height right here? Well, it's not f of 0 like for the left, and it's not f of 1 for the right. So we need values for the right there in the middle between the 0 and the 1, and that is a half. So this one is, where the dot is, 3/2. And this, you can do decimals too if you want. 2.5. And for the last one, 3.5. Right? Let's do decimals, it's probably easier. 1.5. So first rectangle is going to be a width of 1 and height of f of, because we're working with the f's. F of 0.5, which is equal to 0.5 squared. So f of 0.5 plus 1, f of 1.5 plus 1 times f of 2.5 plus 1 times f of 3.5. And then we just need to get the values for those. This is a 1, so that's a 0.5 plus 1. And f of 1.25 is 2.25. You put 1.5 in here and then you square it and you will get that. Plus 1. And 2.25 is 6.25. And plus 1. And that's a 12.25. And if you sum all this, you will get 21. Woo! Look at that. 21 compared to 21 1/3 is so much better than Lram, which was 13.5. Rram. Mram. 21. So much better. So midpoint is always better than the left and the right. So there you have it, guys. That is the midpoint rectangular approximation method. The trapezoid approximation method. Of the 4 methods that are tested on the AP exam, this is the one that takes the most effort to do the setup. The reason being is because you do have to recall what the formula for the area of a trapezoid is. All right. So we're going to go back to geometry skills, and we're going to see if we can recall what the formula for area of a trapezoid is. Right. So in geometry, typically what they give you is trapezoids that resemble something that looks like this, or they might have one of the two sides on the right or left, being flat. Whatever the case may be, the formula for a trapezoid is base 1 plus base 2. You cut that in half, and then you multiply by the height. Now, you say, whoa. All right? What is he talking about? Well, let's go ahead and put some labels on this. The bases on a trapezoid are the two sides who are parallel to each other. So in this case, it would be that line and this line. So you can call this one your B1 and this one your B2. So that's given right there. So whatever dimensions you have for those, you would put them right here on the formula. You cut that in half. And the height is whatever that magnitude is right there. Right? So in this case, that's parallel to this one. So that's your B1, your B2, or your backwards B1 and B2. And your height is just this right here. Okay? Now, the trapezoids that we're going to be working with on the approximations, they are going to be resembling this type of trapezoid, the one that is flat in one of the sides. Another unique thing is that the trapezoids are not going to be drawn this way. They will be drawn with the flat side, or if you call it, the height basically. The height is going to be right here on the bottom. Right? So what I'm really trying to say here is that with the trapezoid, the height is really going to be the width of each rectangle. The width on the LRAM and the width on the right ram and the midpoint. Right? Still confused with this? Just wait until I work out the problem and you're going to see exactly what I'm talking about. Okay? So I'm going to go erase this, move this up a little bit more so we can create more space, and then go with trap. Alright, so you're still cutting this integrand or this graph into 4 sub-intervals, but now you're being asked to use the trapezoid method, or trap. Right? So here we go again. I'm going to make the same lines that we have done with all the previous 3 methods. Now, am I going to make dots here? I mean, we have used dots on the previous 3 methods. Yes, we are. We're not going to do it on the left for the left. We're not going to do it on the right for the right. We're not going to do it in the midpoint for the midpoint. We're actually going to do it on both sides. So it's a combination of LRAM and RRAM. So we're going to put a dot over here, 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 and the last one up there. So I'm going to erase all this. And you're going to connect the dots with straight lines. Oops, let me erase this one. Okay? And you're like, Flores, ooh, I have a feeling that that one is probably better than the midpoint RAM. Well, we'll see. We're going to compute this and see what we get, right? Now, I'm going to work with one particular trapezoid so that you can see how the setup is done, because it's not difficult, but it tends to confuse the kids a little bit more. Okay? So I'm going to grab this one. So that trapezoid, if it was a geometry course, more than likely would be presented to you this way. For some reason in geometry we do that all the time. We present all the trapezoids this way, right? So we always put like the two bases, basically the B1 and the B2, like this. But here, when we're doing approximation methods, we're going to tilt it, right? So if you notice, this is your B1, your B2, and this is your height. Guess what? Once you shift this, you rotate it, then it becomes this. So that height, after you rotate it, is really this right here. And that's why I was saying last time, in previous minutes ago, that this height, it really becomes the width of the rectangle. So this is your height. Right there. And this will be your parallel line with the other parallel line. So these two right here are really your bases. Okay? So let's go ahead and see how we can do the setup for trap. Okay. So that's really B1 and B2. You're not going to be doing all this labeling when you do the AP exam. I'm just trying to see if you can get where I'm coming from with this. All right? So remember, the formula is B1 plus B2, cut it in half times height. Right? So I'm going to fill that in with that particular trapezoid. Right? What is B1? Well, B1 is the height from here to here. So basically, I'm picking up a dot. Right? And how do you pick up that dot? It's really your F of 2. So it's really F of 2 plus the other dot is your other base. So that's F of 3. So that's B1 and B2. And then you cut that in half. And then you multiply by the height. But the height right here is the width. So in this case, that's a 1. So you tell me put a 1 right there. And that is it. I've done the setup only for one particular rectangle. Then we can do each one, sum them up, and that will give us the answer. All right? So here we go. Integral from 0 to 4. X squared dx. It's approximately using trap. Using trap. I'm going to compute the first one here. Right? So what's the height of the first dot? Well, that's F of 0 plus F of 1. You cut that in half times the height. The height is the width, which is a 1. That's the first one. Plus F of 1 plus F of 2, F of 1 dot, F of 2. We're doing this rectangle now. Cut it in half times 1, the height. Plus F of 2 plus F of 3, cut it in half times the height. Okay? I still need one more. I'm going to put this right here on the bottom. Okay? Plus F of 3 plus F of 4, cut it in half times 1. Okay? And that is your setup. That will typically get you a point. The rest is just number crunching. Okay? F of 0 is, I'm computing this right here now. So that's F of 0 is 0 plus 1, cut it in half, times 1. Plus, doing the second one, that's 1 and 4, cut it in half, times 1. Let me see if I can do one more right here. 4 and 9, cut it in half, times 1. So the 1, 2, 3, I need one more. 9 and 16, cut it in half, times the height. So this is just a half. This is 5 divided by 2, which is 2.5. This is 13 divided by 2, which is 6.5. This is 25 divided by 2, which is 12.5. Alright, so that's 3. 3, that's 9.5. 9.5 and 0.5 is 10, 22. So we're picking up 22 from this one as the answer. So trap is equals to a 22. All right. So there you have it, guys. The trapezoid setup. It's a little more tedious. It's difficult. It's really not difficult. The only thing that you have to watch out for is remembering that the trapezoids are not presented to you in a way that, like in geometry, is done, right? And of course, you will be responsible for recalling the formula for the trapezoid. Base 1 plus base 2, cut it in half times the height. I had a few kids that asked me, well, Flores, it's how can I get something more accurate to the answer, to the actual 21 1/3? Because still, 21 was probably one of the best ones. 22 was a little bit, with the trap, was a little bit more off. The right ram was really, really way off. The left ram, really, really low. Well, one of the things that we can do is we can always cut the particular interval into more sub-intervals. So what I have right here, I have presented to you guys an Lram, same graph and everything, but instead of doing 4 sub-intervals, I did 8, right? So if you notice, I haven't done the math here, but I gave you the answer using the Lram, and look, that's a 17.5. That's so much better than a 13.5 when we only did sub-intervals. Will it still be an under approximation? Yes, it will still, because the graph is still concave up and still increasing. So you can see that you will be leaving some little gaps right here. So it will still be an under approximation. For the right ram, 25.5, using 8. 1, 2, 3, 4, 5, 6, 7, 8, right? Is it still an over approximation? Yes, it doesn't change. You can have 1 million sub-intervals. It will still, of course, it's going to be really, really close to 21 1/3, but it will still be an over approximation. Just type it, okay? Look at Lram using more sub-intervals. 19.76. So you kind of get the idea what's happening here, right? The more sub-intervals we cram in there, the better it is. So that's how we get actual answers. We still have not, explored how to actually compute the 21 1/3 mathematically in one shot to get the exact answer. Right? Here's another problem right here, the square root. So you would be working this in class with the handout that I gave you, and you would be coming up with approximations. We're probably going to do this one with 4 sub-intervals. I just want you to get used to doing this setup and doing the number crunching. All right, continuing with approximations. Right? Whether you're doing the Lram, the Rram, midpoint ram, or the trap, all those type of approximation methods will additionally require you to answer a classical question that they will ask you all the time, whether the approximation that you're using in that particular question and the answer that you get, is it a under approximation or over approximation? Now, in order for you to answer that question, you must know what type of a graph you are dealing with. So what I've done right here with this handout is that I have given you some scenarios here. Basically, I'm telling you what type of function you're working with and the type of RAM or method that you will be using, and your job is to figure out whether you're using under approximation or over approximation, right? So it's quite a bit of things to remember, but you don't have to memorize stuff like this. You can just do a quick sketch of the graph that you're going to be working with, and then sketch the RAM that you're working with, and then it will come out. The answer will be there, right? So right here you have an increasing and concave up. So increasing and concave up, and I'm only going to work on the first quadrant. So increasing and concave up. So there you have it. And they want me to use a Lram, right? So I'm going to cut this. Look, I'm just doing sketching here, right? Boom, boom, boom. Right? I do not need those lines to go past. Okay. And since I'm using Lram, the dots need to be on the left side. So dot, dot, dot. There's my rectangles. You can see that that's actually a under approximation, right? Now, did I have to recall that? No, I didn't. I just had to know what the process was, do a little bit of sketch, and the answer will be there. That it is connecting the dots in AP calculus, right? Let's try one more. Increasing and concave down. Now, increasing, right? Concave down, and then, all right, so here we are. They want me to use Lram. So let's Lram, dot on the left side. Dots on the left side. You can see that this is a under approximation. Same graph, but I want Rram. Dots need to be on the right side. So you can see that this is really going to be a over approximation because those little corners are going above the graph. Okay? So the technique is the same. So you have a function that is decreasing and concave down. Decreasing, concave, concave up, I'm sorry. Decreasing, concave up. So I'm decreasing and concave up. That's exactly what I'm trying to draw there. Right? Decreasing and concave up. There you have it. And I want to use Lram. Dots need to be on the left side. That is a over approximation. Right? At random, right? Now, do I recall what I did on the first problem? Increasing concave up. I don't. It was Lram, Rram. It's very confusing, right? So it's better to learn the strategy on how to sketch this, and then the answer, I promise you, it will be there. We will be practicing a lot more on this in class so that you can get that additional point on the